Okay, good day. This is Math 140 College Algebra. I am Professor McCulley, and this is the um, presentation for Lesson 7.1 Definition of Logarithms. Let's get right to it. So today we're going to recognize and evaluate logarithmic functions with base A, and I will tell you what base A means here in a moment. We're going to graph some logarithmic functions. We're going to recognize and evaluate the graph of natural logarithmic functions. And the natural logarithmic functions have to do with base E, which is the Euler's number from the PERT equation in the last chapter, and we're going to use logarithmic functions to model data and solve problems. So first, why should we learn logarithms? Well, when we look at this first equation here, we have a variable that is an exponent. And this one is fairly easy to solve because all we need to know is that if these two things have the same base, then the exponents would have to be the same. So 9 is actually 3 squared. And so 3 squared has to equal 3 to the x. We know that x is equal to 2. But this part is a little bit more difficult because 10 is not a perfect power of 3. Now we can say that it's probably a little bit more than 2, and 3 to the third is 27, so it's definitely less than 3, but it's probably closer to 2 than it is to 3. But other than that, we can't come up with a real good um, estimate of what x is going to be. So we can use logarithms to get a very accurate value for x. So definition of logarithm, log a of x equals y if and only if a to the y equals x. And since it's an if and only if statement, it works both ways. So let's look at it this way. If I said 3 to the fourth equals 81, that would be the exponential form. And we can say a, well, the a is going to go there, so log of 3, x, well, x is that value there, so it matches up to the 71, or it's not 71, 81. Come on, Macaulay, get with it. And the y and that y match up, so the 4 has to go there, and this is the logarithmic form. And the way we read this expression is we read it log base a of x equals to y. So we have some simple properties of logarithms, and I don't know why these aren't showing, but we will bring them up here real quick. There we go. Look at all that. That looks good. So using the definition of logarithm, we can say that log base a of 1 always has to equal 0 because of this definition. If I change this logarithm to exponential form, I'll get a to the 0 equals 1. And we know that a to the 0 is always 1, provided that a is not equal to 0. Similarly, if I go a to the 1 power, I will get just a. If I go a to the x power, I'll get a to the x. So they have to be equal. Similarly, log or a to the log base a of x equals a. And if I have two expressions with the same logarithm, or with a logarithm that has the same base, then those expressions have to be equal. And that's very similar to the exponential property, where if I had a to the x equals a to the y, then x has to equal to y. It's the same type of concept, it's just with logarithms. And this one is also going to be very important to us. If I have log base a of a to the x, I'm just going to get x, and that we're going to use quite a bit, especially with the natural logarithm, which I'm going to talk about in a moment. The generalized logarithmic function is an inverse of the exponential function, and we talked about inverses a couple times already this semester. And remember, um, most of our functions and operations that we've talked about so far have inverses. Addition has subtraction, multiplication has division, square has square root. Well, 2 to the x has excuse me, log base 2 of x. So these two functions are inverses of each other, and we can see that because if we put in this line y equals x, and we fold it along that dotted line, I'll get it eventually. If we fold it along that dotted line, the red and the blue curves would match up, and we'd get purple, but that's for art, I suppose. All right, the natural logarithmic function. There are two what I'm going to call known logarithms. So these are our known logarithms. And the reason that we know them is because they are on your graphing calculator. If you look over here, next to the 7, there's a log, and next to the 4, there's ln. And on most scientific calculators, you will have those two logarithms. And so you know those values. And ln is log base e, and log with no value down there is log base 10. And the reason we hate the natural logarithmic function is because there'll be a lot of times when they're going to ask us to solve an a equals pe to the rt, where we're trying to solve for one of those two variables there, either the r or the t, and the ln in conjunction with this property right here that we had on the previous page is going to make things a lot easier. Now, the reason that we have the common logarithm, log base 10, is because that is what our number system is based on. We have a base 10 number system. Every time you move over a place in a number, you move up by or down by a power of 10. And so they're known because they're on your calculator. All right, so a couple of examples here. Change the exponential to logarithmic function using the definition of logarithm. And if we remember, log base a of x equals y if and only if a to the y is equal to x. So we will just switch these numbers around in this place and change them into a form that looks like this. So we'll have, let's see here, log base 2 of 32 is equal to 5. That looks good to me. All right. And then they want us to do the opposite. So similarly, 3 to the 4 has to equal 81. And if they ask you to change the logarithm to exponential form and it's not a valid logarithm, you've made a mistake. So, or not a valid exponential. This is a true equation. If you don't get a true equation, then either the problem's wrong or you made a mistake. It says evaluate the logarithm without using a calculator. And so if they're asking you to do that, 4 and 64 are both perfect powers of some similar base. And so what we're going to do here is we are going to set this thing equal to y. And so I'm going to set it equal to y, and then change to exponential form. And so 4 to the y equals 64. Now, the only way that these two things can be equal is if we can find a power of 64 that is a base of 4. Now, 4 times 4 is 16, and then 16 times 4 is 64. So note that 64 is equal to 4 to the third. All right, so we can replace that. We can say 4 to the y is equal to 4 to the third. Since the bases are the same, the exponents are the same. And y equals to 3. So log base 4, do it again, of 64. Oh, come on, quit it. Log base 4 of 64 has to equal to 3. All right. Next, it says given the function f of x equals log base 2 of x and g of x equals negative log base 2 of x minus 1 plus 3, describe the transformations from f to g. All right, so I'm looking at that and I see 3 transformations, 1, 2, 3. And so we're going to do it just like we've always described transformations. We're going to pick a number, plug it in, and see what happens and how we would evaluate it. Now, just as a note, logarithms are evaluated in the order of operations at the same level as exponents. So, and that has to do with the fact that they're inverses of each other, just like addition and subtraction are done at the same level, multiplication and division are done at the same level. So logarithms and exponents are done at the same level. Excuse me. So let's say I pick x is equal to 5, and what happens when I plug 5 in there? Well, the first thing that's going to happen is I'm going to subtract 1. Now, when I subtract from the variable, we remember that that is going to be a shift 1 unit right. All right, so we're going to shift 1 unit right with a subtraction by 1. After we've calculated that, we're going to do the logarithm. That is the function, so everything that happens after that is going to happen to the y values. And so I'm making it negative, and when I make the y value negative, or I make the function negative, that is a reflection in the x-axis. And then after I've done that, I'm going to add 3, and since I'm adding 3 after the function, that's going to be a shift 3 units up. All right, next it says use properties of natural logarithms to simplify this expression, and I picked this one especially because this is something that you're going to see over and over when we're doing logarithms, and especially solving for exponential, solving for functions where we're trying to figure out what the variable and the exponent is. LNE, so I'm going to say recall that the ln is equal to log base e. All right, so we can rewrite this as log base e of e to the 2x. And now we're going to have an instance of this property that I said was important. Remember? So log base a of that same number. So if these two numbers are the same, it's equal to just that exponential value. And that is, again, very, very powerful and very important for the future. So also recall that the log base a of a to the x is equal to x. So we can say that the log base e of e to the 2x is just 2x. And that is very powerful. All right, last one. Professor McCulley has designed a faster than light FTL drive because I love science fiction. The number of times the speed of light that the drive can achieve can be modeled by the function L equals 0.23 log of the quantity g plus 1. Now recall, I need a C in there. I didn't do a very good job, so let's do that. Recall that log is log base 10, and that is on the calculator. So we can calculate log base 10. So the first question here says, how many times the speed of light would the drive produce if 50 gigawatts of energy was put into it? So if I go through this, L is the number of times the speed of light, and G is the number of gigawatts of electricity. Well, if they give me 50 gigawatts, or gigawatts, I don't know what it is, gigawatts. Let's say gigawatts. All right, 50 gigawatts, that's a G. Excuse me. I can plug this in and just do that calculation. So for part A, I just have L equals 0.23 log 50 plus 1. All right, well, that's a calculable value, 0.23 log right next to the 7, and I can do 50 plus 1 in my head and make it 51. And I can say that that is, oops, I made a mistake. It should be 0.23. So second entry brings that back up. So let's make that into a 3. There we go, enter. And we would say that it is 0.393, 0.393, and L is times the speed of light. All right, now 3.93 times the speed of light means that they're actually going slower than the speed of light. If I got 1.0, that would be 1 times the speed of light, or actually the speed of light. So part B says, how many gigawatts, so I'm looking for G, would you need to put in the drive to travel 2 times the speed of light? So 2 times the speed of light, again, I'm plugging in, so I'll have 2 equals 0.23 log of G plus 1. So I have to solve this thing. All right. So I can't do anything with the definition of logarithm as long as I don't have a coefficient of 1 in front of the logarithm. So note divide by 0.23 to get log by itself. All right, so I'm going to have, when I do that, let's give me a little more space, I'll have 2 divided by 0.23. Now I could calculate that, but it doesn't really matter. I'm gonna do it all in one step once I get G by itself, equals log of G plus 1. Now remember, log is log base 10. So if I put a little 10 there, I can use the definition of logarithm and say that G plus 1 would equal 10 to the 2 over 0.23. And use definition of logarithm. All right. And now I just have to subtract 1, and I have G equals 10 to the 2 over 0.23 minus 1. And this minus 1 becomes almost insignificant. So let's go to our graphing calculator. 10 raised to the 2 divided by 0.23. And then I need to bring it back down, minus 1, hit enter, and I get, oh, that's a big number. I'm not going to write all these digits. So let's see here. There's thousands, or hundreds, thousands. This is millions. So we'll call it 496.2 million gigawatts. 496.2 gigawatts, approximately. Well, that's all I have for today, folks. So the Marvel fun fact of the day, in Spider-Man Homecoming, Kenneth Choi played Principal Morita. And here is Mr. Principal Morita in Spider-Man Homecoming. But he also played Howling Commando Jim Morita in Captain America First Avenger. And there he is. So they got the same actor playing 2 different roles. And the Easter egg is that when they were in this scene in Spider-Man, you can see this guy's grandfather, who he has a memorial for in his principal's office in the high school, which is kind of cool. Although you have to be really, really nerdy to see it. And hey, it's me. What are you going to do? Have a good day, folks. That's all I got. Bye.